Good evening, ladies and gentlemen. It is time to start our next discussion of our next unit. We are going to talk about waves and sound. Okay, so what exactly are waves? A wave is a disturbance that travels through matter or space, carrying energy without matter. So remember, it's carrying energy. Light and sound are both types of energy. Just like in the last unit, we talked about heat being a form of energy, light and sound are also types of energy too. Mechanical waves, like sound waves, need matter to travel through. Without matter, there is no sound. I'll explain in a few minutes. Remember once again, waves do not transport matter, they transport energy. Okay, on your paper you have a picture exactly like the one you see here. This is a wave. We're going to go over a wave structure. First, you're going to label the parts of a wave, and then we'll write down their definitions. The first part of the wave is called the crest. The crest is the topmost portion of any wave. The lowest portion of any wave is called the trough. The amplitude is about half of a wave. And the wavelength measures any one given point to another given point. It's easiest to measure wavelength from crest to crest. Now let's go over those definitions in words. The crest is the highest part of a wave. The trough is the lowest part of a wave. The amplitude is how far any point of the wave has moved from its beginning point. This is equal to half of the wave height. So from the crest to halfway down to the trough. Keep in mind that the more energy that is in the wave, the more its amplitude is going to be. The higher the amplitude when there's more energy. A wavelength is the distance from one crest to the next in a wave. So a wavelength would be from one crest point to the next crest point. Let's take a pit stop and check out to see what Bill Nye has to say about waves. Okay, now back to where we left off. Thanks, Bill Nye. Okay, so we were talking about waves and wave structure. So frequency. Frequency is the number of vibrations in a given time. We measure frequency in a unit called hertz. If the frequency increases, the wavelength decreases. So if an object is vibrating a lot, or if we have a sound where you're hearing lots of vibrations, it's going to have a high frequency. Notice how the higher the frequency is, the smaller the wavelength, the smaller the distance from crest to crest. So it has a high frequency if there are lots of crests in a given space. Let's talk more about sound waves. Sounds are produced by the vibration of objects. Remember, matter has to be in motion for sound to be produced. A person's voice, like you can hear me right now, is produced by the vibration of my vocal cords. So I want you to take a second. Take your hand and put it on your throat. Say hello out loud. You can feel the vibration of your vocal cords in your throat. Now whisper it. Hello, hello. You don't feel that vibration anymore. The reason why your voice is quieter is because now you just hear the air pushing through your mouth. There's no air moving through your vocal cords. No movement of vocal cords, no sound coming through the vocal cords. In the picture, you see a piano and a guitar. They rely on vibrating strings to make the sound. Even though you're hitting keys on a piano, inside of the piano, there's these tiny little hammers that are hitting strings. And that vibration of the hammer hitting the string causes the sound, like your finger plucking a guitar would cause the sound. Remember, once again, matter itself is not traveling through the wave. It's the energy that travels from molecule to molecule. In the Bill Nye video clip, you saw all those that looked like little air hockey pucks that were hitting one another. It is not the matter itself traveling, it's the energy causing one molecule to vibrate to the next. Not all of the energy is passed from molecule to molecule. Some of this energy actually gets used up in the random motion of air molecules, and some of it's lost as thermal, which is heat energy. The energy of a wave decreases as it travels. Sound gets quieter and quieter the further it travels from its source. And thank goodness it does. What if you could hear every single sound in the entire world at once? It would be really, really annoying. The further you are from a sound, the quieter it is. That energy decreases as it gets further. All right, so in the Bill Nye video, we left off with an echo. An echo is a sound reflected off of the surface of another material. So like when you go into a cave and you say, hello, 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 you're hearing your voice bounce back to you because your sound waves are bouncing off of the cave wall and coming back at you or bouncing off of the other walls in the cave. Another important vocabulary term is reverberation. This is when a sound wave is reflected off of many surfaces at once. All right, let's admit it. How many of you sing in the shower? We sing in the shower because it makes the sound richer and fuller. You see all of the tile in the shower wall? It's a perfect place for singing because your voice bounces back to you. Have you ever been in a noisy room? Usually a noisy room that has lots of reverberation has lots of angles and hard surfaces. Lots of places for those sound waves to bounce off of each other. Nice, quiet rooms usually have soft surfaces like upholstery and carpet. If you've ever checked out our own choir and band rooms, have you seen all those like weird tiles on the walls? Those pieces of fabric? They're not there just to be pretty. They're actually to catch sound waves, so there's not so much reverberation while you're practicing. Pretty cool, huh? Science and music together. It's awesome. Pitch. Pitch is the perception of a frequency of a sound being high or being low. The higher the frequency, which is the faster vibration of the molecules, the higher its pitch. Loudness is the perception of the amplitude of a sound wave. The more amplitude, which is energy a sound has, the louder it's going to be. Hey, that word amplitude. Where's all my guitar players out there? Ever heard of an amp? An amp is an amplifier. What it does is it amplifies or makes bigger and gives more energy to your sound so that it's louder. So think about it. You use an amp to make your guitar louder. You're giving it more energy. Amplitude is measured in a unit called decibels. We can hear decibel sounds, or decibels are measured from 0 to in the thousands. We can hear anything as soft as a whisper, which is in the 5 decibels, and then you can hear up to the thousands. But anything above 140 decibels is really damaging to your hearing. One more thing we need to talk about is something called mediums. A medium is anything that a wave must travel through. It can be a solid, liquid, or gas. Remember, it's energy traveling. We need matter for that energy to pass through. The different mediums affect the speed of a wave. The closer the molecules are, the easier the sound can travel. It's easier for sound waves to go through solids than liquid or gases because the molecules are closer together. Well, we're at the end of our notes, and no Mrs. Walter notes could be complete without an explosion. So let's test this idea of mediums with an explosion video.
Does sound travel faster in the ground or through the air? And is the speed of sound ever as fast as the speed of light? To find out, you need to make a sound that can travel a long distance. 5 tons of plastic explosive should do the trick. How would you detect sound waves in the ground? Samantha's going to watch for the explosion, but she's wearing headphones so she can't hear it. Fung is going to listen for it, so he's wearing a blindfold. And Elizabeth's going to detect sound waves in the ground.
Ready? Ready.
So, who's going to be the first, second and third to detect the explosion? They were waiting to see the light, hear the sound, or feel the sound. Samantha was first because the light got to them before the sound. Elizabeth was next when she felt the sound coming through the ground. And Fung was last when he heard the sound of the explosion coming through the air. The speed of sound in the air is 350 meters per second. At 5,000 meters per second, sound travels much faster through the ground. But light is much faster than any sound, at 300 million meters per second.